All right, I guess I'll take it away. So this is, I'm going to talk about 3D printing with Forth. I actually, a bunch of this was stuff that I did actually almost 3 years back now. At the time, I meant to give a talk about it, never did, and thought I'd use this opportunity to do that. Oops. So I'm going to give a brief intro to 3D printing, talk about how G-code and printer control work, talk about CSG and sign distance fields, and then talk about how I use Forth to generate a path for the printer, and a project that I actually used Forth for something useful to fix my microwave. So 3D printing is actually super old. It's actually there's been efforts in 3D printing going back to the 1950s at MIT, but modern 3D printing, a lot of it stems from the RepRap project. It started in 2005. That project had an interesting goal. They basically tried to devise an open source set of tools for 3D printing and a design for a 3D printer that was open sourced, where you could use the printer to print all of the non-standard parts needed for the printer itself. So you could print all of the various plastic pieces that were not sort of just extruded aluminum, things like that. And someone else could take those parts, get their 3D printer set up with the addition of what they refer to as vitamins, the extruded parts that are not sort of producible by the printer. That produced lots of iteration and interest, and there's a variety of different designs that have come out of that project. One of the more popular ones is the PRISM i3. It's sort of the canonical example of a rectilinear printer. It moves the bed in, slides forward and backward, and everything happens in XYZ sort of rectangular alignment. One of its innovations was that it was one of the first with a heated bed, which one of the challenges with 3D printing as you're building things up is getting things to stick, but not stick too much. And heating the bed actually helps quite a bit with that. Around the same vintage, there was a design called a KOSSEL, which is a delta printer. It's built around threefold symmetry, and it actually emphasizes having the parts of the printer be more stationary to allow for faster head movement. It originally used a glass bed. This is my 3D printer. It is actually derived from a KOSSEL. It's a cheapy knockoff of a KOSSEL that I got in a kit for I think it was under $200. It's not exactly like a vanilla KOSSEL. It has a heated bed, and I was attracted to it because of the sort of natural simplicity of the Delta design. The motors, there's four stepper motors that go, three of them in the corners to control movement of the head, and then a fourth for movement of the filament that gets pushed out through the head. They drive a bunch of belts that go up and down the three columns, and then those three columns are attached by a little armature to the head. And because the head doesn't have any motors or anything heavy in it, it's able to move quite a bit faster than is typical for a rectilinear printer. The electronics are squirreled away underneath the bed. I can imagine in the original glass design, this was a good place to put it. I have mixed feelings about this choice with a heated bed, because if you can imagine a very warm metal bed on top of your circuit board, it's a little bit disconcerting that you've got a heat source directly above that. Nonetheless, it is an effective printer. I have to say, having put one together and played with both this one and several that I have access to at work, there's a lot that you learn by putting one together, especially about sort of the fussy aspects of maintenance of it. You'll notice I've got this masking tape down on the print bed. This is because, again, the sticking to the bed is a sort of an essential aspect of getting the thing to work well. And I found that the masking tape helps with that process to give it a slightly less sticky surface. The print head has fans attached because, again, you're emitting melted plastic, and you want it to be melted when you want it melted, and you want it to cool down quickly. And so having fans continuously blowing at the extruder as it comes out works really nicely. And you get out interesting results. You can see sort of the banding of the layers in them. One thing you'll notice that is a problem with all 3D printers, but is especially a problem with Delta printers, is the little hairs that you see between things. Because the printer head, the motor that moves the extrusion is so far away from the print head, you end up not being able to have as precise a control as to the stopping and starting of the flow of filament. And so you end up with a little bit of a trail, even when you sort of meant to turn things off. Tuning it and care with it can reduce the problem, but it's a bit of a challenge in general with that approach. If you have the extruder closer to the print head, you get a little more precision with that. And here's a side view of the thing. There's two major materials that are commonly used. There's lots of different things you can put into a 3D printer, but PLA or polylactic acid is a popular one. It's made from organic things. This is the sort of plastic that you get in a recyclable utensil. It melts at 155 Celsius, although with all these things, you want to air a little hotter so that you get things sort of at the right flow and viscosity and cool down rate. Another popular choice is ABS. This is actual plastic, the stuff that goes into Legos. Runs a little hotter. I myself use mostly PLA, actually almost exclusively PLA, because of a very simple reason. The PLA, when it is melted, it smells. The description people often use is sort of pancakes with maple syrup, which is a relatively pleasant smell. The ABS smells like melted plastic and kind of what you would expect. It's just a very unpleasant smell to be around, and so that's the main reason. I haven't had projects so far that I've needed the ABS is slightly harder in the final result, but yeah. So give you a sense, this is what it looks like when it's printing, and it's able to do that very fast movement of the head because it doesn't have to move anything around. It's nice that the bed is stationary, and most of the moving parts are stationary and so on. One of the very first things that I printed for it was actually a terrible print because it was one of my very first, but it's a spool holder so that I can attach a spool of filament up on the top. Within 3D, the RepRap derived 3D printing community, the ATmega 2560 is a very popular CPU for the control boards. I think this is just because it has lots of I/O, and this is a domain where lots of I/O is important. With 54 digital I/O pins, of which many of them, depending on the model, can do PWM and lots of analog inputs. It helps for all of the devices that you need to control. And so on the KOSSEL, for example, you need to control a display. You need to, it has an SD card slot. It has temperature sensors and temperature controls for both the extruder and for the bed. It has 4 motors to control, and then it has a bunch of end stop sensors to help it in self-calibration, getting into the right, figuring out the relative position of things. I've misspelled firmware because that's what happens in slides. But the firmware that runs on the board is Marlin. It is an implementation of the G-code language, which we'll talk about in a second, and supports sort of a very rich, full version of that language. And it supports both tethered and SD card operation, which is nice because then you can just turn the printer on its own and print from an SD card, which is nice once you've got a design sort of figured out. G-code has been used also going back to those early efforts in the 1950s, but it wasn't standardized until the 80s. This is a single letter code that lets you describe a path for the movement of the various motors that are used for extrusion and movement of the head, and as well as a bunch of parameters like the speed and things like turning on and off the temperature controls and sort of using them like a thermostat. This is what it looks like. You've got comments in here, but basically the M commands are sort of escape codes for particular operations like temperature control. The G codes are specifically around movement of the motors and are by far the most common, the bulk of the file. The reason it's called G code is in fact because the G's are so prevalent as the first command. A G1 in particular is linear interpolation between 2 points, and you simply provide a bunch of points to move the head to, and then it linearly interpolates between them. And this includes the path of the filament to control extrusion. So how do you then take this and build a model out of it? Well, you need to have some way to describe the 3D structure you want to build. There's lots of options: platonic solids, meshes, and NURBS and voxels, but one that is especially effective for physical objects that you want to build is the CSG. CSG is the idea of taking a bunch of primitives and then using intersection and union and difference and operations like that to combine them to describe the ultimate shape that you want to build in a sort of a tree. And you can readily transform this into something that's expressible in Forth. What I've done in the sort of domain-specific language that I've used is use some simple words for the shapes, and then I use a geometry stack to describe the hierarchy of objects. And to be clear, right, the idea is that you need to be able to union and intersect, but also translate and move around things to get them into the appropriate position. I use an approach for units that's actually, I think it's mentioned in Thinking Forth, which is the recommendation that you sort of use the smallest unit you're interested in this case, micrometers, and then in everything else you can express as a scaling factor on top of that. And then going the opposite direction, you need to be able to print these out. I use 4 variables to track the position of the head and figure out where I want it to move. And then you're actually able to use sign distance fields, which is a technique that can be used to as a way to implement constructive solid geometry. The idea is that you have a function that describes how far you are away from the surface of the object. So you have a positive number if you're outside the object, a negative number if you're inside the object, and right at 0 is on the surface of the object. So for example, here is a sphere, and your distance from the sphere at whatever radius gives you your sign distance value for that sphere. You can implement this in a single line of Forth, and a cylinder is not that much more complex. And you'll see here that the yellow is the negative region. You get more negative the deeper in you go. The blue, as you get bluer as you go further out. And then right at 0 is the surface of that object. You can do something similar for a rectangular prism. And again, in a one-liner, you can capture that here's this rectangular prism. And then operations like union are actually very simple. They're just the min operation. The intuition here is that the minimum, if you've got 2 different sign distance fields, picking the minimum of them is saying that you're picking the shortest path of the 2. And so that ends up being the union of either. And the converse is true. The max is the intersection. You're picking the longest path of the 2. And so then you end up with the intersection of those sign distance fields. And then you can do negation to get the inverse, so that you flip what's inside is outside and what's outside is inside, flipping positive and negative. And then you can combine inverse and intersection to produce difference. And so, for example, here subtracting one sphere from another sphere to get a hollow sphere. Transformations aren't hard either. You can express those just by manipulating X, Y, and Z. And then you need to have a geometry stack so that you can save your place in a certain position, go do a set of transformations, and then undo that by popping things back off the stack. This lets you build up complex shapes, and you get an interesting looking sign distance field out of it. But what you really care about ultimately with a solid object is just once you've gone negative, you know you're inside the object, and once you're positive, you know you're outside the object. And so you've got this these building blocks that can be built up to build more complex objects. You then do what in 3D printing parlance is called slicing. You need to be able to flood fill each layer to figure out where to move the print head. And, or rather, sorry, you need to do a plan for each layer. And to do that, I use a flood fill. And with 3D printing, you generally don't want to have your movements be aligned. You don't want a stack of horizontal lines covering each other because that won't have good structural strength. So I do the simple trick of alternating the flood fill so that it has a horizontal versus a vertical bias. And then I represent the positions as a single number to make it convenient to put them on a stack. So an X value plus a Y value times a slice length. And then as you're doing the flood fill, you simply emit G-code operations to describe the path that you have found within one layer. And then you need to keep a stack to be able to keep your place and get another stack to keep your place within the flood fill. And then I've got a few words for my horizontally biased sweep where I favor the X direction and then the Y direction versus the vertical one where I favor a Y direction versus an X direction. And then the main loop for the flood fill it's a little complex by fourth standards, but it's not too bad. You're basically looping while you have a region yet to flood. You pop off one additional point to flood, check if you've gotten there in a bitmap that you need to store of each layer, and then do your horizontally or vertically biased step in each direction, and then emit the G-code operations to cover that region. So let me talk about the project that I applied this to for a real thing. I had a broken microwave. The door on my microwave, the latch stopped working, and it's because the holding spring and the latch, the piece of plastic that was holding the spring and the latch broke. And so I wanted to replace this with a piece of thing printed with a 3D printer. And I decided to use Forth because I had already implemented some of this code to do this and didn't have anything to use it for, and thought, well, this would be perfect. I could get out a piece of modeling software and do it, but I was worried about measurements and specifying everything numerically, and modeling software lets you do that, but it's actually kind of tedious. You have to go and select each thing, and with Forth, I could just enter, here I want a cube of this dimension, and then it's at this offset and so forth. So to give you a picture, unfortunately, I didn't take good pictures at the time, and I now live in a different place, but I found someone on the internet, as one does, that had exactly the same problem or nearly the same. And here he's got the spring removed. This is the piece that it goes inside of the latch of the microwave, and then sort of in there. And then if you notice, there's this little piece of plastic down here where it's sort of burst out with a loop, and right in that spot. And I needed to replace that piece. And in my case, it actually broke off completely. His, it looks like he just sort of lost part of it and needed to attach the spring somewhere else. And so unlike his, where it has this kind of a lumpy thing, or actually, at least this is the replacement part I found in the internet, mine actually had a single circular shaft that needed to move up and down. So I ended up going through four separate models before I got one that was sort of an exact fit. Initially, I thought, oh, I can just wedge in a cube and it will fit tightly. On the first one, the hole, it doesn't show here in the hole, but I had the extrusion rate too high, and so the hole actually ended up getting kind of warped and filled in more than I wanted. On the second one, I made the hole much bigger, and then added a little flap to try to hold it at the right position when inserted into the slot. That ended up not working, so I moved the flap to the front. That worked kind of okay, but I ended up realizing I wanted it to be thicker, and also that a second flap would give it more stability. And that one worked, and I was able to use the microwave for a good year after that until I sold the place and actually in the process yanked out the microwave. This is these are not the originals. These are ones I reprinted the other day from the model that I still had sitting around, and or from the G-code file I still had sitting around. And this is the sort of progression of what each of them looked like. It was not a bad process at all. I think I spent maybe no more than 2 hours, I think, on it in total. To give you some idea of the complexity of the code, it's really not too bad. This is the entire thing to print that fourth model, so a little setup code for emitting temperature control, some boilerplate. There's those operations for intersection and union and so on. The geometry stack, the flood fill, and then the main loop and the code to describe the 3D model. Are there any questions?
That's really cool.
Wow. In my notes, my summary is wow.
I agree. Brad, was this part available commercially or was it obsolete?
The issue is that if I had, actually, I don't know. I was not able to find the exact piece commercially. It was a fairly old microwave. I believe it actually came with the place, so it was certainly at least a 15-year-old microwave. So the answer is I don't know. My sense is that it was part of the whole framing of the door, and so I was replacing a piece that was chipped off of it rather than the entire piece. It may be that I could have purchased the entire frame, assuming that the fact that I found someone with a relatively similar microwave online. The interesting bit is that even the sort of the rest of his microwave setup looked, the furnishings around it looked so similar to my own. I'm kind of suspicious that it was a cookie cutter design for the whole kitchen setup or something. So yes, possibly out there, but given the alternative was replacing the microwave and the hood, I thought, well, I can see if I can fix it. It may have been I could have fixed it with some simple metal part, but it was partially the fun of finding a piece that would just plug right in.
Yeah, I've had the experience recently where the control for my cooktop used to be available direct from the manufacturer through one of these various websites or from a local appliance parts place. And then it became obsolete, so I bought a generic one. And now the generic one is obsolete. So the most recent round of this is now going to be buy a new cooktop, I think.
Yeah, it's a gratifying thing to be able to replace a thing. I'm not sure that there's a certain sweat equity aspect of the fun of it, but yeah, I do think for certain, I have prior to this, had appliances that have broken and had to spring for the part or spring for the whole replacement. So now, the next time I have one of those kinds of things happen, I may think, hey, I'll see what I can produce on the 3D printer.
Hey, Brad, another question. So what does your software do? Does it like create the G code file that you give the 3D printer?
Yeah, so this is the output of the program is a G code file that is then copied onto the SD card, and the printer prints it itself. It would in principle be possible to maybe run something directly on the ATmega, and that might be interesting, but that was a whole other layer deeper. And I thought, well, let's start with emitting G code because it's a common thing, and see if I can get that aspect of it right. And then, as I mentioned, this is work that I did 3 years ago, and by some strange twist, never managed to put together a fig talk about it. But.
Did you manage to implement all the basics G codes that a 3D printer requires, or a subset?
So it's the other way. It's because I'm emitting G code, I only needed to emit the subset were relevant for me. So being able to turn on the temperature, turn on the fans, move into the home position, and then the movements of the head and the movements of the extruder. And so I used a trivial subset of the total. And so if you were controlling the thing directly, you almost certainly don't need the G code offers, a huge set of commands that are probably more flexibility than you need in total, but I would imagine it depends on what you're doing. And G code is used across a lot of domains. It's used to control CNCs with all kinds of attachments. So it's the other thing is that the G code file that I emit is probably not the smallest G code file you could emit for the same task. So it's wasteful in terms of the size of what it's emitting because of not taking advantage of those richer commands.
Would you be able to print something more complex, like this one? I printed this one on my head printer. Would it be possible?
In principle, yes. The set of models that I've described, in this very simple CSG language, have their limits. One, I would say that something that's more complex seems like it would be feasible. One potential limitation is that right now I'm computing a sign distance function without doing anything to sort of short circuit it when you get as you combine things. So the cost grows linearly in the size of the model. And that's not ideally. What you would do is once you're sort of outside of a certain region, you would want to have like a bounding box and exclude that region, or otherwise what will happen quickly is that it gets slower and slower to generate the more complex the model. So in principle possible, but the object you just held up looked super complicated. I can't imagine without a modeler sitting there. But on the other hand, for mechanical parts, one of the things I found is that even just putting them in a modeler like Blender, until you've kind of printed them out once and really gotten the tolerances right in terms of them fitting together, it's actually kind of hard to know how it will fit together in total. So hard to say, right? Like I imagine, did you print that item out I assume in a series of separate pieces and then assembled them, right?
Yeah, it's not that complex not that complicated. It's kind of complex. You got these one. They are probably the most complicated ones to print. But then you have these are quite simple, and the same with these, and that's just a base plate. So it's not that it's not that complicated, except for those. Those legs.
Actually, as you held it a little closer, right, some of those pieces looked actually like, well, that's a prism, and then there's a cylinder and a cylinder out of it. And so for those kinds of pieces, I think it would probably not be too bad. One other caveat I should mention is that on traditional slicer software, they do a nice job of they fill in with some sort of a fill pattern, and then they surround the object with a path that goes around the edge. And in principle, the sign distance field approach would allow a way to do that, but I haven't done that. And so I essentially end up with a print where the exterior is rougher than you might get out of a traditional slicer, because it doesn't have that nice extra stroke that goes around the exterior to give it a smoothened edge. And that's actually unfortunate, because with the Delta printer, one of the nice things about the Delta printer is that it because it has these kind of circular movements because of the threefold symmetry, it ends up having nice rounded edges on all